Yeah, hello and welcome to our lecture series on climate protection. First of all, change in our program. Please be aware that on the 24th of June, Engelbert Portenkirchner will present his lecture on powering the energy transition. This will take place not here in the Audimax, but in the lecture hall just on the opposite side. It's the Kleiner Hörsaal. Yes, and this lecture was shifted. Yeah, and today Karl-Heinz Erb is our guest about the second Austrian assessment report on climate change. This was published last year in June, as you know. It's the most recent comprehensive climate assessment for Austria. Unfortunately, we didn't have the opportunity to present the results immediately after the publication, but you all might have heard about it in the media. Austria is warming faster than the global average, up to now already 3.1 degrees centigrade since 1900. And unfortunately, Austria is not yet on pathway consistent with its long-term climate goals. Achieving climate neutrality requires accelerated action across energy, transport, industry, buildings, agriculture, and consumption patterns. Today, Karl-Heinz Erb will present the structure and the main outcomes in brief. His focus, however, is on the report's central cross-cutting themes, the land use, which is both a source and a solution. It fits well to our last lecture on rebutting peatlands. Karl-Heinz Erb is the head of Institute of Social Ecology at BOKU in Vienna. One of his fields of research is ecology, land use and land cover change. He was coordinating lead author of Chapter 2, Climate Change, Land Use, Ecosystem, Services and Health. Welcome, Karl-Heinz Erb.
Thank you very much. Sound is okay? Yeah, thank you. Thank you, everybody. Now I just have to change. Maybe you give me a hand on changing. Yes, this one. It doesn't matter. Okay, so thank you very much for the nice introduction. I'm gonna talk to you. I just have to orient myself in this big room with not so many people here about the second Austrian assessment report. And as was said, I'm gonna focus mainly on land use issues. And this is what you see here. It will be about many assets. It will be about the place where we stand, and it will be about the things that we eat and many other assets. But first of all, a little bit back to the very roots, to the fundamentals. What are we talking about today? We're talking about climate change. We're talking about the science of climate change. And here you see a few iconic figures, and I hope all of you, many of you are completely aware what you are seeing here. On the left-hand side, you see the components of the climate system. Right-hand side, you see one of the worrying things going on, but not the only one. This is the increase of CO2 concentration in the air. And down below, you see something which is new, which comes from the new assessment report of the IPCC, of the International Panel on Climate Change, Pathways to the Futures. Many of you might have read newspaper articles in recent times that things have been changing between now and the next year, so the next assessment report cycle, that we kind of think the above red path is not very plausible anymore because we have a full speed global layout of renewable energies. But we also know that this bluish one downside is not happening neither. So good news on the one hand, we are not as bad as we could be, but the not so good news is we are also not far as good as we could be and as we need to be. That's the thing. Having that said, let me just jump a little bit into what is actually an assessment report. An assessment report is a very particular type of text. An assessment report is not a review. It is not a compendium of papers like a cumulative book, where book chapters write about different things. An assessment report is a text which evaluates, which has the task to evaluate the state of knowledge. So it is related to a review, putting things together, but not just putting them together and making a story out of it. This is the knowledge gap, and therefore we propose to move on like that. But it puts everything together, and it offers an assessment. It offers an evaluation. What do we know? With which level of confidence? This is what IPCC is doing, and IPCC is the role model we are following here. IPCC has 3 phases. There is a scoping phase, which is done with the governments and with scientists. Then there is point 2, the multi-stage peer review. Scientists write texts. They are open to review for experts. Many reviews are collected. They come in. There is a procedure how to integrate all the review comments. So experts write about glaciers, other experts not involved in the assessment write, but you might not be right because this and that. Every single comment has to be answered by the team. This is quite a lot of effort, and you will see the scope of the Austrian panel later. The next stage then is the country approval. This is the approval session. And in the approval session, it's not just the experts. In IPCC, there are many experts, so it's a delegation of experts, but they sit together in a room with national representatives. And for the most important texts, the key text is the summary for policymakers, they go through the text word by word and approve it word-wise. So if somebody does not like a certain wording, last time we had the problem of writing fossil fuel phase out. If nations do not like that, they might object. And there is the need for a process which reconciles the wording, which comes down to a level where kind of everybody agrees, or at least nobody puts a veto forward. This, of course, waters a little bit down the science side, but this is an assessment report. This is not rocket science. This is an assessment report. It waters a little bit down on the science side, but it increases national commitment. Once, well, we have seen, at least to a certain degree, some nation states agreed to subscribe to something. They cannot say, the scientists have written that, we are not okay with that. There was the country approval, and the delegates from IPCC will say, but on the day this and this, and in this minute, you gave green light for this formulation. So this increases the commitment. And this is also what makes, in my eyes, the IPCC so important and so much working, despite this inclination of being quite modest in its claim and very much focused on robustness of knowledge, on lowering down uncertainty. I was part in the IPCC special report on land use change, and I can tell you this was a particularly interesting experience. The day of the national approval, I wasn't part of the delegation. Everybody gets an email that you have to stay at your phone at this and this time. And when some nation experts like to know something about whatever, you will maybe get a call which you have to pick up. You kind of commit yourself that you pick up the phone and you answer and discuss whatever is to be discussed. I was not phoned. I was happy about that. Well, here you see the international IPCC, and down here you see, and now we make a jump, you see the Austrian IPCC crew, part of the crew. This is part of the kickoff meeting. This took place here in Innsbruck of the Austrian panel on climate change, of the crew writing the second assessment report. And you see in front sitting the 4 co-chairs. The co-chairs are the chiefs, if you wish. They manage everything. They don't write themselves, but they organize the process. They are critically assessing the drafts. They are saying, this does not sound too balanced. Maybe we need another expert. That's what they do. And with the exception of this country approval, well, Austria is one country. With the exception of the country approval, everything, all the rules of the IPCC are also followed in the APCC, in the Austrian process. How does it look like? These are the key 8 chapters. You can read them yourself. They cover nearly everything. Yeah, some of them are more sectorial, like industry, energy, transport, and up down. This bluish one, this is climate change, land use, ecosystem services, and health. This is where I was coordinating lead author together with two colleagues, one from Innsbruck, Ulrike Tabainer, and the other one from JASA, Wilfried Winnivater, and we organized this chapter. And then down here, we have others focusing on governance, focusing on transformation pathways, on scenarios, on discussing what do we know about what is working in the future and what is maybe not working so well. That's what we did here. And you see about 800 pages have been written. 200 scientists have been involved from about 50 institutions. There have been many external reviewers, international reviewers. The texts have been written in English. We got about 4,000 comments. And as I said to you earlier, also in Austria, we had to answer all of them. It's not allowed to say, yes, interesting point, but we don't deal with it. We have to substantiate everything which is put there, or you can rebut it. You can, of course, say, yes, might be true, but this and this literature does not say what you are saying. And we have to be very careful in separating opinions from facts, from knowledge, from scientific knowledge. That's actually the core of what such an assessment report does. Important, you see the website here, and you can just go to the net and type there ARR2. All these texts are open source. So this is I would even say, tremendous resource for students, for advanced students particularly, because you get two things. First of all, you get a review of nearly everything related to the climate. You get the text for free, and you do not only get a review, who has written what, Focus Austria, but you get an assessment. Where do we have agreement? Where do we have disagreement? Where do we have knowledge gaps? Postdocs, dissertation students, if they hear knowledge gaps, they should think about, oh, that's a paper I'm gonna write. I know how to answer that. Okay, so this is what this text is about also for academia, but the text is not written for academia. The text is written actually for policymakers, and that's why we create also two texts, not of this rigorous scientific style and tone. One is the summary for policymakers, which is a very succinct, a very short, to the point conclusion, what we know and what we don't, and what we should do in this level of uncertainty. And then we write a technical summary, which is kind of an intermediate thing. It's the most important things, but it's not everything which is written in the 800 pages. This is much, much shorter so that you can have a start, that those people who are experts, but they don't have too much time of reading everything, and of course we know not everybody is always interested in everything, you can select in reading whatever you like, and you can have an easy jump into that. Okay. What is the focus of today? This is how assessments reports have been written. I'm gonna focus with you now on the chapter I was co-chairing with my two colleagues and with about 15 to 20 other writers, some of them contributing, some of them lead authors, some of them contributing lead authors. So there is a hierarchy, if you wish, of authors writing this text together. And what is the content-wise theme? Well, the content-wise theme, and it was already nicely addressed, is when we talk about land, when we focus at land from a scientific point of view, land is a very particular resource. It is not just a resource which is there, and if we don't use it, it stays there, and if we use it, it gets less. But once we start playing around with land, we play around with systems. We call them land ecosystems. And playing around with land ecosystems has consequences for the dynamics of the land ecosystems and for society. And we humans very fundamentally depend on land ecosystems, very much. The food we eat is probably the single most important resource, which is irreplaceable. We do not have a substitute, at least for the moment, but to eat stuff from ecosystems. This makes it quite important because everything what we do with land might somehow affect our food system. And our food system, think back when you go home or when you go out drinking beer. Well, the food system is quite close to our human beings. It's very close to our to the physical world of our being. And therefore it is very important. And we in science talk about a triple challenge when it comes to the relationship of land use and climate change. First of all, land ecosystems are closely interrelated with the climate system. Well, ecosystems are defined as the sum of biotic and abiotic factors in nature. So actually the climate is part of ecosystems. And if changes in the climate system occur, also changes in the ecosystems will occur. And we will discuss this very shortly. But then, and we will also discuss this shortly, land is a pervasive driver of climate change. Land is not just there, but by using the land, we create climate change. And you have heard about that. There are emissions from land, we have deforestation, we have methane emissions from rice and from animals and so forth. And lastly, that's the third part, land can provide very massive, very rapid carbon sinks. So what is a sink? For those of you who do not know it, sink is actually more or less the description of the direction of a carbon flux, of a carbon flow. Everything what flows from the atmosphere to somewhere else, we call a sink. There's a land sink. It can also flow to the oceans. Then we say it's an ocean sink. And if you wish, sink is the flow, opposite flow to an emission. Yeah, with an emission, we emit carbon from land, for instance, to the atmosphere, and the sink is the other way around. And this is the important thing. Land can provide sinks depending on how we have used land in the past, depending on whatever is going on in the climate system. It can provide strong sinks, very strong sinks. But of course, these sinks, as nothing in ecology, comes for free. Everything is kind of connected to everything else. So if we change something there, we will have changes somewhere else too. And this is actually what we have been assessing in this chapter too. We still stay a few slides global, and then we go to the Austrian reality. So land use is a driver of climate change. This is the radiative balance, if you wish. This is radiative forcing. So how much the climate has been changed from the past, from something like a pre-industrial era to now. And you see these bars, and the bars to the right-hand side, the positive, this means these are emissions. These are changes, climate changes, warming. And the bars to the left, which are in blue, these are not warming, but they are the opposite. These are coolings. This is global cooling. Yeah. And land use now is related to a lot of these bars, and two of them I marked. But before we go into that, two key terms, which you have to keep in mind, because they will pop up all the time, and it's good that you maybe scribble them down if you're not familiar with them. One is AFOLU. This is when IPCC talks about all things I addressed now shortly in the introduction, they call it AFOLU. Well, we all like acronyms in science, and AFOLU is the acronym for agriculture, forestry, and other land uses. So this is everything what is happening in the land sectors. Yeah, there's another term which comes more from the accounting world and not from the sectorial world, which is LULUCF, which, if you wish, simply speaking, is the FOLU part of AFOLU. So you have agriculture, forestry, and other land use. And forestry and other land use has two names, FOLU, or land use change, and forestry. Yeah, these terms will pop up. I will use them from time to time without thinking, so maybe it's good that you memorize them. Okay, globally, about 20% of the emissions we see here in the upper side come from AFOLU. Deforestation gets rid of carbon. We have animals, we have rice, which emit methane. We work with the soils. We wet them or drain them, and this releases nitrogen compounds, N2O, for instance, all heavy greenhouse gases. we have to be very careful, and this is why this LULCF, why so many terms are there. We are talking here with this 20%, this is a net flux. This is not the overall emissions of everything. This is if you take globally the balance, the saldo of emissions from deforestation and the carbon sinks we have in other places of the world. In the tropical south, we have a lot of deforestation going on and we lose carbon, we have emissions. But here in the global north, in Austria, up to the last year, we had a carbon sink. And this 20% is already saldoed there. So the emissions are larger, but land is currently acting as a sink. And then you see something else here. You see to the blue side, land use actually even leads also to global cooling. Why? This is actually the first principle, the first mechanism discovered and discussed in science about land use. We didn't understand the carbon cycle and the nitrogen cycle and all this stuff 50, 70 years ago. But we knew already then that if humans change ecosystems from one ecosystem to the other one, usually from a dark forest to a brighter cropland or to cities, we change the albedo, we change the reflectance ratio. And actually with that, somehow we are lucky in all the bad luck we have, that we have a global cooling effect due to land use. Yeah? And this is actually the much older described mechanism we have here. But to make the thing a little bit more complicated, just at the moment, I told you the emissions are on net terms, the land use related emissions, the AFOLU emissions, 20%, 23%. Doesn't matter so much. It's about that. It's also not so easy to really write it, really calculate it. But at the same time, land acts as a sink. We have something like a sink function on the Earth. And this is because we did some calculations, we, not me, others did some calculations. They took the balance of everything we know, all the emissions which go to the atmosphere. We can measure that. We know how much stuff we burn. We measure the carbon concentration in the air. And we recognized not all carbon which we emit ends up in the atmosphere, in the carbon stock. There is only a so-called airborne fraction, which is about 45% at the moment, yeah? And about 55% end up somewhere. The first thought was everything ends up in the oceans, but then ocean scientists made some calculations and said, we don't take it all. We only take half of this 55%. And we don't know where the rest goes. The rest goes somewhere, but we have some suspicions. As it is not the atmosphere and not the oceans, it might be on land. We understand quite well a lot of ecosystems very well, but we don't understand some ecosystems so well globally, the forests. So there is a suspicion, but more by exclusion than by understanding, that the forests react to climate change. It's getting warmer, it has more CO2 in the air. They react by increased growth. And increased growth might create larger stocks. Not necessarily, of course, because only growing does not mean that you get thicker. You can also metabolize more. But there is the suspicion that it is the forests and probably the forest biomass, but maybe also the forest size. But having that said, that is something we cannot do anything about it. This happens, and we can be lucky. And Johan Rockström, one of the scientists now, he's the director of the IASA, of the International Institute for Applied System Analysis in Luxembourg, close to Vienna. He says, we should also not meddle with this phenomenon of land sink, because this is something we should be lucky to have it. This is a resilient response. The biosphere is helping us. It's getting warmer, it's getting more CO2 in the atmosphere, and there is a mechanism which buffers it. And we know many of these mechanisms in the biosphere, and this is another one which was discovered something like 50 years ago. Enough of that, we will not discuss this further. This is a very important thing. This is also a reason why so many things are so complicated in the land system. We now talk about the emissions. But having that said, this is challenge 1. Then we have challenge 2, climate change impacts plant growth. And here you see a map. First of all, we see on the left-hand side, if we have global warming on the average, the warming is much, much stronger on land than on the oceans. The land gets warmer. That is also one reason why now us having something like 1.4 globally, maybe 1.4 something globally, we have about 3.1 in Austria at the moment. This is because land gets warmer than the ocean. And the ecosystems respond strongly. And here I brought you this map from the 1.5 degrees Celsius report by the IPCC. And this tells us, and look at the colored areas, the gray areas function the same, but these are only small changes in the ecosystem. But the colored areas, these are ecosystems which change drastically with climate change. And in red, the red area changed already with 1.5 degrees. The yellow area, they change with about 3. That's where we are right now here in Austria. And then the green ones, they start only changing with 5-degree warming. But if you look at this map, understanding that the land ecosystems get warmer than the oceans, look at the Alps. Look where we are. There is quite some severe changes going on. And this is something we don't understand too much of it. But this is, of course, pressure on our food system. This is, of course, something which will affect the global yields of food. And we live in a luxury society, if you wish, here in Central Europe. We have kind of food security reached, not all of us, but most of us, and on the average. But look globally, we don't have food security. Yeah, food security has a lot to do with distribution, access to food. We have enough food globally, and still having enough food globally brings some people to undernutrition, undernourishment. And now you think about yields going down globally. Will it ease the system? Probably not. So this is quite a severe challenge ahead of us. And then the third challenge is, and here I brought you 2 slides, left-hand side still the 1.5 degree report. Most scenarios to the future, which kind of say, check, can we somehow guarantee a 1.5 degree world? On the left-hand side, you see, most of them, they kind of need a rapid phase out of the fossil energy, which is the gray area there. And some scenarios, in particular the P4, this is a scenario where we still love fossil fuels because we are kind of techno cool guys and we stick to our whatever we do because we have ideas. And one of the big ideas is we can suck out carbon from the atmosphere with bioenergy. We can put it into other compounds and we can put it to the mines or to the deep sea. We can put it away from the atmosphere forever. This is something where this is kind of, there are some prototypes. This is called BECCS, bioenergy fueled carbon capture and storage. This is actually as prototype somehow working, somehow. The problem is, first of all, we need a lot of more energy to run it. And then we have to replace ecosystems with bioenergy plantations because we need bioenergy and we cannot create bioenergy out of nothing. We need plantations for that. And you can think about this yellow area. This is the BECCS area, which somehow guarantees that we save the planet climate. This creates something what we have called in the past the land squeeze. We know that we live in a world where actually land, the entire planet is more or less used up. We have land use on 3/4 of the Earth's surface today. We use the land. And now another player comes into being, which needs area. And what might happen with our problems of food security if another demand for biomass comes up? Large scale, look at that. This is about the same amount as fossil energy. It's quite a lot of stuff. We replace the emissions by area equivalent of the fossil energy. This is quite a lot of area. People have calculated this is the area of the North American forests taken together. All North American forests we need to run this system. And now you think about the food system, and then you think about something we did not discuss in the assessment report here or not discuss deeply. We live in a world of biodiversity crisis as well. And biodiversity has to do with land use. And if we want to go to plantations, biodiversities usually and plantations do not go so well together. Be it palm oil, be it something else, it's not so easy. They're not good friends. And we call this the land squeeze because we have different demands for the land, and we somehow need to squeeze this land through all these demands. And on the right-hand side, you see an iconic figure which we developed for that we have. This is a proportional flow of all biomass running through the ecosystems and society. So society, this is the blue bubbles, livestock and P for the human population. So this is more or less proportional. Well, more or less, not with the land side. Only a few people know that we humans have less mass than our cattle. Our cattle, this is a cattle planet in the meantime. Yeah, about the mass of the cattle and the humans together are about 95% of the mammalian mass on the earth. So the wildlife, all the whales and the giraffes and the lions and you name it, all the mammalians, 5% of the total mass. The rest is us and our livestock. And of course, we somehow need to change this in order to make this land squeeze working. Now let's switch to Austria. In the next half hour or so, I will talk about impacts, which we discussed. And I will be short here because this is not my full expertise, and also because I want to focus a little bit more on the GHG emissions and on the mitigation options land in Austria provides, what we know about that. So, and then afterwards, after the mitigation options, I will summarize and show some of the key trade-offs and also synergies which we have. This is how it looks like, the assessment report. And we heard this nicely. This is the development of 150 years of temperature development. This is the global average in blue, and this is what happens in Austria. This is the 1.4 blue line and about 3 something in the year 2020 here in Austria. This is the most iconic figure IPCC developed something like 20 years ago. These are the so-called burning embers. And how do they work? Each of these columns, you see they are shaded. They are shaded in yellow. Yellow means something like low risk, not so much, we don't know if there is an impact, and up to this red, dark red, even violet, this means very high impact. And here you see a selected realms, we would call them dimensions of how we are affected. And what do we see? First of all, we see already with this 1.5 degree, think about 1.5 Celsius, think there. Most of these bars are red yellow. So we know something is going on. It's maybe not too severe. And then think about what happens when you jump up to the 3. It's getting red almost everywhere. There is one exception, which is the grasslands, and this has many issues. We will not discuss that. It's also not to show you that, but we have a problem. We have a problem in agriculture. We have a problem in health. All these things are discussed. So this is not, if you wish, rocket science, something completely new under the sun. We discovered it. This is the summary of the state of the knowledge, because there is something else more hidden in this figure. Look at these little dots here, confidence level, these grayish bars here. Look at that. If you look at that, you see that as long as we are down in the white, easy yellow area, we have a lot of dots. We have 3 dots. 3 dots means a high confidence level. This means we have many studies and we have a high level of agreement among these studies to understand what is going on. And the higher we go, the fewer dots we see, which means the warmer it gets, the more we also enter scientifically, academically, uncharted territories. We don't know what's really going on. Uncertainty is increasing as well. This is a key threat. Well, this is a key task also for science. This is why we are all standing here in university. But this is something where a concern or a certain pressure on the policy making side emerges. But being a little bit frank, taking decision in times of uncertainties, this is what politicians are paid for. I don't know for how many centuries, but this is actually what they do. They do decision making in terms of uncertainty. But we are now in a era or phase, you might call it however you like. Think back, what happens when we have uncertainty in the climate system? What will people do who like to stick to their way of making money? They will say, oh, as long as it is as uncertain, no need to change. We don't know. Maybe it gets white, everything here. So uncertainty is a political challenge as well. Okay? There are some much more detailed stories here. And there is, sorry. We see, and here you see for Austria, and this is a work done here in Innsbruck by Uta Schirpke and Erich Dasser, Ecology Institute. We see that not all ecosystem services, so the things ecosystems do for humans, if you wish, very anthropocenically, we can discuss this later. Some of them even improve. Some things get better, because if things get warmer, other things can get better as well. Productivity, for instance. A lot of productivity can be enhanced when it's getting warmer, as long as there is enough water that's actually working. And this is something what we see, and this is this bright yellow area that you see some of the ecosystem services. There is an inventory. I'm sorry that this is in German. I just made a mistake by preparing this. Some of them increase, but most of the ecosystem services, be it the provision of agricultural goods, be it forestry, be it in particular cultural services, are actually going down. And they are going more down the warmer it gets. Well, this is a no-brainer, but here it's not about detecting new things. Here it's about saying, what do we know? And this is relatively well understood, and you see the confidence levels with the stars, and you see some things we understand quite well in the Austrian global arena. Tourism is, of course, for instance, just to highlight, there are always winners and losers. Well, tourism, winter tourism will get into problems. Summer tourism, maybe not. But it all depends on the extreme events. If we have nice warm summers, is good. But if it's getting too hot and too dry and too droughty or too stormy, hurricanes and stuff in summer, nobody knows. This is the level of uncertainty we are dealing here. Having that said, we are in a planet under pressure, if you wish. Now we think, what is land use doing with the climate system? This is the second part of my talk. And here I show you the summary for policymakers, summaries of the summaries, what has been going on in the emissions in the past in Austria. You see these colored areas, these stacked areas above. You see how they developed over time. And you also see that we have something like a peak around the 2000s. And since then, we have a slight decline in emissions. Yeah. And then you see also down, if you look down, you see there is the lowest LULUCF. We discussed this term already. In the past, particularly around the year 2000, this was a heavy sink of carbon. And it improved the balance drastically. But look how this went on. We lost the sink. Over 20 years, the sink disappeared. We will later discuss what happened. Down there, I have brought you the individual developments. So this is just a breakdown of the stacked areas above. Now, if you look at the stacked areas to the right-hand side, you see what the future might bring. These are different scenarios. How much pathways, different pathways are there? Some of there, and I bring a slide on that, what are we doing here? But before looking into the future, let's look into, oh no, this is the future now. What will the future bring? This is the same slide as before, but with much, much more detail so that I can tell you and show you that we do more than just showing simple graphs. So there's quite a lot of material there. This is a comparison of the political commitments out there for Austria and what the result of these political commitments, if you put them through a model, tells us. And there are 3 levels of making scenarios. The first one is WEM. You maybe not have heard this, WEM, WEM. This is called the scenario with existing measures. All measures which the parliament has approved to go for, the governmental decisions. Yeah? And you see that with existing measures, it goes down a bit. It goes down maybe 30%, relatively slow, and then it levels off there. The existing measures, well, good direction, but not enough. Then there are others. This is the WAM scenario with additional measures. This group of scenarios, this is the sum of all decided things and all the proposals which have been done on the governmental level. You might have heard that the governments write green papers and white papers, and some groups say, but we could do this and that, and others say, yes, but we need an assessment before. If you all take this together, so it's not decided, but it's somehow discussed already. This is this with additional measure, and you see we come down to something like 22 to 23-ish. This is megatons carbon emissions. So we are still far away from net zero. So 0 is something else. Now we are about 76, 80, left-hand side, yeah. And 73 here in this case. We had some increases in the last years. And then you see it goes down. And then the Environmental Agency of Austria has said, well, this is not very satisfying. Now we take everything together, what we have, and it's still not enough. Let's think ambitious. And thinking ambitions, they created a scenario which is called EEA, Environmental Agency Transition. This is a massive scenario of transition. And what happens in this transition? It's much more radical. It results in a reduction of 92%. Still not enough. We are still positive. We are still not net zero. If we take not just together what was decided, what people, governmental people are discussing, but if we take everything together, what the Environmental Agency thinks is somehow plausible and doable and manageable. Which calls us, of course, what else can we do? Which tells us, the problem is big and we don't get rid of it. Let's keep it there at the moment. But I promised you that I show you also the emission balance, the highlight emissions from the land sector, from this AFOLU sector. And you see, agriculture, this is part of the agriculture is up here, it comes later, has an emission fraction of about 10%. This is what the methane and the N2O and many other things, mainly from our animal and agricultural systems, are going out from the manure management. If we look at the LULUCF, the land part and forestry part, so the land use change, you've discussed last time moors. This is part of this LULUCF, but not about what could be done in restoration. This is still what is happening. The LULCF in the last 5 year average was an emission. Well, we still lose forest area. We still lose tree areas, let's put it that way. We still lose moors, we lose carbon. And if you look at the line here with forests, you see that there is something else going on. And this is even more drastic. We had an average sink of about 1.3% of the total emissions in the 5 year average past us. But in the last year, the balance flipped. And today, the forests are emitting carbon in a share of 6% of the total emissions. And we have to understand this, and we have to do something in the light that we do not achieve the net zero target, that The problem is getting bigger, kind of, or staying big regardless of what we do. We lose the one thing which once was a very strong sink, kind of automatically, if you wish. That's not true, but let's be a little bit bold. And here on the right-hand side, sorry, I forgot, you see the agricultural blue arrow going a little bit downish. We improve. Indeed, we have a reduction in the livestock sector. We have less animals running around. Very slowly. We need more, but it's the right direction. But we have this loss of this carbon sink in forests. That is what we are facing today. Before we go into, and I speed up a little bit, before we go into mitigation options, we need to understand, and this is a bit the complex figure at first sight, but I will talk you through, and it's not so complex after all. We need to understand what is actually happening. And what is happening in something what we call the biomass flows. So here you have something like a Sankey diagram. Some of you might know what that is. Sankey diagrams are diagrams which trace materials running through different nodes, through different systems. And they help us to understand what are big things and what are small things. And what we see here, first of all, there are a few very big nodes. I don't know if I don't have a laser pointer. The mouse is not, maybe the mouse is working like that. One node, well, I talk you through, it doesn't matter. I don't need the mouse. One node, the wood system. The wood system is large in domestic extraction. This is the dark green up there. But the wood system is also large in terms of imports. We get a lot of resources from outside. From the globe, mainly from Central Europe, but not only. We also get Russian wood and Brazilian wood, also there. Yeah. A next big node, of course, is the livestock system. The livestock system, this is the down there, this turquoise color, the bedding and the livestock system. This is one of the biggest nodes in the entire system. And in the biomass system, and many people are surprised by that, the energy system, the biomass burning, is tremendously large. It is actually larger than the total forest harvest in Austria. We burn more biomass than we harvest biomass in Austria, you could say. How can this be? Well, we import so much biomass, we refine it, we send products to the rest of the world, and we burn the residues. And sometimes we pretend burning residues is carbon neutral, but that's not the case. If burning residues, there is carbon in biomass, of course. It's more complex, and we will discuss this later. This is something we need to keep in mind, and the stars, then you can have a look at home if you're interested. These are now the summaries of the emissions related to the biomass flows and on the big nodes running through here. What happens, and now we go to the forest, what happens to the forests? I have showed you we have this slight reduction in agriculture, less animals. The LULCF sector, particularly the forests, have been massive sinks. 25 million tons. You have to think the emissions are 75 million tons, and 25 was the sink, the negative saldo. Yeah, this is quite massive. And it tells us a little bit about what the size of potentials could be, kind of potentially. You will come to that later. Yeah, but since the 2000, the sink function is lost, and it is now, and you see, it is somehow oscillating around zero. So where does this come from? What is this net sink? We have to understand a little bit, not so complicated. It's very simple mathematics, but they are quite complex ecological processes. What is a net sink? When are we growing? Well, we humans are growing when we eat more than we metabolize. And forests are kind of similar. They are growing when the growing part is larger than the dying part. So when more trees get thicker than the trees which die because they're old. And what happened behind this line? Increment in the past went down a bit. We don't know exactly why. One thing can be that we have better measurements. Yeah. The other thing is the forests are getting older, and we know when organisms are getting older, usually they are growing a little less. Yeah, can be also that. Yeah, and we have climate change. We have a different climate with whatever, and this might also affect growth. But in the end, it's getting warmer, and warmer would need more growth. So it's not clear, but we have a small decline in increment. I think I brought you this one. Yeah, this is the green line here. You see, it's more or less the same. But we have a tremendous increase in mortality in the dying part, but actually not in the dying due to, let's say, extreme events. These are the dark pinkish areas here. These are the annual extreme events. So when forests have been hit and stand replacingly, so that standing trees have been cut down. Yeah, and we see about between 1/3 and maybe from year to year 1/2 of the total forest harvest was due to salvage, was due to extremes, was due to these disasters, if you wish. Yeah, but we have a tremendous increase in this brighter area, in the plant harvest. We're harvesting more and more. And now let me be a little bit frank. We can, of course, wonder why the zinc goes down when we harvest more. But in the end, there is not so much to wonder about. If the balance is the zinc is the saldo of increment and mortality, and we increase mortality, but we cannot increase increment at the same time, we will lose biomass. And this is actually what was happening in Austria the last 30 years. Now I move on. What can we do? And I look a little bit into the big scheme. This is from the summary for policymakers. So this is the synopsis of the mitigation options. These are all the mitigation options which have been discussed by these about 200 people. You always see two bars, or not always, but most of the times. The upper bar is the upper bound. So this is a kind of a very optimistic assessment of mitigation potential. So how much climate change we could avoid if we would do that. Yeah. And this is in million tons CO2 equivalents per year. It goes up to about 30, keeping in mind we have the emission of 75, let's say 70. This is about 1/3. The total size of one bar is maximum 1/3. Yeah, and then the lower bar, this is the more conservative estimate. So to be sure, what we really understand. And this is much lower. If you look at wind, the upper bar, wind can really go up very high here if we are optimistic. Some provinces do not give us a lot of reason to be optimistic in the wind implementation. And so therefore, these potentials are lower. Okay. If you look at the AFOLU part, and then there are these shadings. These shadings, the yellow shadings, they're the costs per unit of ton of CO2. How much we would have to pay for this type of mitigation. Of course, there's a lot of uncertainty involved. I will dig into that into detail. But the key message here is there is not one silver bullet. Let's do that and we save the climate. A single bar is usually, if it's a large one, it's about 10. So this is about let's say 1/7 of the total emissions. And if we go very optimistic, it's maybe about 1/3. But then we have to be very optimistic and many things have to fit together. So key message number one, we need to do a lot in many sectors. Actually, we cannot miss out any of the sectors. All of them have to move because otherwise this does not reach. And think back, I told you about the with additional measures and the transition scenarios, they do not reach the net zero. Such an implementation in a sense would reach net zero, but of course it's already kind of something where we have more wishful thinking than knowing how to implement it. Okay, so this is the first one. The second one, and now we look at this blue thing. This is what I draw here around. This is the AFOLU sector. So again, the land sectors. And here we find many and some relatively big, let's say in the quite strong realm, and particularly those which are strong on the lower bound. If you only look at the lower bounds on these bars, you see those which are really big, you find them in the land sector. And don't get misused by these gray shadings. These gray shadings do not mean that we don't know how big the potential is. They mean we don't know a lot about costs. Nobody has ever assessed costs. And again, think back, we do an assessment report. We don't do our own science here. So this is the summary of the existing body of literature, which we bring here. Okay, having that said, let's go through this part, and I will just jump through all of these and give them a little bit in proposition. So first of all, mitigation potentials in agriculture and human nutrition. Here we find technical options, humus layers, nitrogen efficiency, covering manure with sheet and things like that, has positive effects, but they are moderate, if not small. Another one, which is quite bigger, is if we would find a way to reduce our food waste. There are quite a few studies showing this quite stringently. It's not so easy to implement, obviously, because, but we see it already could bring up to 4.7 million tons of CO2. And then we have the big elephant in the room. If we would be able to shift away from our heavily animal product defined diets towards more plant-based, this does not mean everybody needs to go vegan. This means we need to reduce it a bit. We still can have meat. We did these calculations, and down here you see a comparison of this, and this is global, so this is not the Austrian one. The Austrian one, the business as usual, so the 2012 and TSS would be a little bit larger. We did the calculation of a diet which was proposed internationally as a safe planetary diet, the Eat Lancet diet it's called. And here you see how it looks like. First of all, it has a little less calories. Well, that's not so bad compared to what we here eat, not compared to the African and Indian continent. It has not so much red. There is still some red inside. Red is the meat and the animal products, the milk, but it has other protein crops, particularly nuts. It has nuts there. People have been making jokes that this is making us all nuts, this diet, but let's see. And if we translate this diet into the global, into the Austrian reality, hypothetically, the result would be that between 5 and 15 million tons of CO2 can be mitigated relatively quickly. Why quickly? Well, the mechanism behind that is we get area free and things start growing, but growing is slow. So this is not immediate, but we get rid of a lot of animals and immediately we get rid of a lot of N2O and CH4. At this very moment, we don't need it, we don't have it. So half of this, you could say, is very quick. The rest, and I don't know half or not, something in between is very quick, and the other one needs time. But we have some knowledge gaps. Economic feasibility. What does this mean for farmers to produce less animals? What does this mean for the entire farming system? We know a lot of subsidies go to animal husbandry and not to plant-based production. We have to change many things and not just one, also politically. We don't know how this will change the rural sides. There's even no study about that. Yeah, so we have to understand this better. We don't know what this does, what such a change would do with the cultural ecosystem services, because if we have less animals and we want to make a carbon credit out of that, we need somehow to put carbon to the ecosystem. More forests, a closer landscape, and not the open landscapes we like and tourists like. There will be some changes, drastic changes here. And of course, depending on how we do it, there will be impacts on biodiversity, on ecosystem functioning, and many things. Because just that we say, let's put more carbon to free areas, to freed areas. Well, somebody has maybe the idea to put miscanthus plantations there. Don't know how biodiversity friendly that is. So we have also to find good ways of implementation. It's not so easy. Forestry. Let's go a bit quicker. If we change the tree species in forestry, and this is something we have to do kind of anyway, you all know that climate change is also affecting the trees, and some trees are not so adapted to warmer climates than others, so we have to change them. And by doing this wisely, we can create a intermediate to small mitigation potential of 1.9 million tons. We can have, and this is what is propagated a lot in the forestry sector, shorter rotations. Let's produce more wood, let's cut the forests more often, because then we have bioenergy, and this bioenergy can substitute for fossil fuels. The calculations which have been done by colleagues tell us the opposite. Shorter rotations means less carbon stored in the forests. The forests are kept much younger and much smaller in carbon terms. And the substitution effect cannot compensate for that. So we have actually shorter rotations means an emission boost of 6.8 million on top of what we have already. Not a good way to go for climate protection. Maybe a way to go for climate forests adaptation, because we also have to change the tree species in a forest. And how can we change tree species? Well, by chopping down forests and planting new. So we have a trade-off here. Then we have using wood more efficiently in a cascade, burning less and keeping more in material. Data tell us there are important things to get there, important potentials, but not so big. But again, another elephant in the room, quite a big potential, up to 8 million tons of carbon CO2 equivalents per year we can get by letting forests get older. For instance, increase the fraction of unharvested stands from today 1.2% up to 5%. Additionally, reduce 10% of harvest in commercial forests. Seems to be not so much, but of course 10% if you own a forest is still 10%. But if you do so, even by factoring in that then you have less material and less biofuels to substitute for fossil energy, you create a mitigation potential of 7 to 8 million tons of carbon. This is big. This is 10% of today's emissions. And this is something which happens immediately because the forests are growing. And if we harvest less, they grow more because the forest sink is the balance of increment and harvest. And if the harvest goes down and the increment stays the same, the sink case at the proportion goes up. So this is something which can act immediately. And we have to decide if this is a way to go. This is a drastic change of how we think about forests in many regions, and particularly in the mountainous regions like here around Innsbruck. But this is something we have to think. Can we afford not to use these potentials? Do we have enough other options out there? Here I made a mistake. And I will shortly also address here that this is heavily contested, also in the scientific community. And we wrote another, and this is where I was co-chair, another report. This was a special report in German on land use and climate change. And here we kind of depicted the different positions which are out there on how to use forests in the future. And actually we have two schools of thought. There is one school of thought, and you might have heard that a little bit from how I am reasoning here. People who say, let's change and reduce harvest intensity for the moment because we need the sink and we need it now. Others say, no, we cannot afford that. We cannot change the forestry sector. It isn't very important what happens. The forestry sector, every sector needs to be net zero themselves. And if the forest sector is net zero, the others have to do the same. Something like arguments like that. Yeah, there is not an easy way to find really out what is there, but we also find, and this is also task of an assessment report, we found some lines of commonalities. And one commonality where there is almost no difference in the standpoint is burning wood is the least of the options. Burning wood for heating is not a good carbon solution. Using wood for material performs much, much better. You see here, this is from the Forestry Institute. if we increase energetic use, our mitigation potentials are much smaller than if we use material. Everybody agrees on that. That's very important to keep in mind. Another point of view is wood energy today is mainly there for room heating. But for room heating in the meantime, particularly if we roll out photovoltaics, has much better, much more energy efficient options. So we can get room heating in much better ways than to burn wood. And we can leave wood in the forests, at least for now, to buy us time. But as I said, there are some common grounds, but there is a debate still going on. And this is the background of the information which I brought to you, and I need to be quick here for the sake of time. There is not a lot of confidence about these findings. Why? Because we only have one study in Austria. And this is the result of this particular study. And we in IPCC and APCC, if there is only one study, we say low confidence. We need more studies. We need more studies with different approaches. But we only have this by UBA, by the Environmental Agency, and by BFW, by the Forestry Institute. And this is kind of the result, what happens with different scenarios, how to use forests with the carbon sink in the forests. Negative means it is a sink, positive means it is an emission. The reddish line, the black line, and the blue lines, they are kind of typical ways how to handle forests, changing tree species, having shorter rotations. Then you see the business as usual. This is the gray and the black line. This is if we just do the same as we do now. And then we have the green line. This is when we reduce forest harvest by about 10%. And when we increase the unmanaged forests. So this is not even what forest ecologists or whatever people have calculated. Forest people have calculated this. And now, if you take the balance, this is only the wood side. This is only the forest side. If you look at the bar, this is the summary. And if you look at the saldo of everything, which are the solid bars, you see that in particularly up to the year 2110, so something about like 80 years to the future, let's be simple. This is the much more advantageous scenario in terms of climate protection. That's what the people tell us here. Yeah, I do not have time, but we can maybe discuss this later. This has led, and I wanted to show you and read you this, but maybe you have a look at home then. In the assessment reports, we have to find a common language. And if it's not easy, in the moment, it's not easy to find a really good common language, one starts to become very dry in the formulation so that everybody can subscribe. And therefore, we wrote here a sentence which starts at the blue part and ends by the end here. And it starts with contrasting two scenarios and changing this to that and this to that and making everything very complex. But in the end, the message is we have a strong potential in forests. We can harness these potentials relatively immediately. It is effective at the moment we decide for going it, but it does not come for free. It comes with a drastic fundamental change in the forest sector, which we have to do. And to summarize this, here I brought you some lines. First of all, the technical options are there, but they are small. The easy things are small, unfortunately. Changing biomass, reducing biomass, be it in food, be it in forestry products, particularly forest energy. Think back, the biggest node is forest energy. This would be a way to go. But there are synergies and trade-offs, and this is my last part. I try to be quick here. We have seen this shift towards less animal products brings a lot of climate change advantages. It also brings health advantages. And I brought to you an older slide published in Nature something like 10 years ago, where they show that less animal products in food is good for many things in human health. We all know that, but science tells us. Yeah. It helps to reduce deforestation. And with less deforestation, we reduce also zoonotic diseases. So we have quite some health impacts. And burning less wood, we see the climate stuff before, but it also reduces indoor pollution and outdoor pollution, Feinstaub, particulate matters. Yeah, so there are many reasons at the health side. I'm quick here and about to finish already. We have seen that land is limited, but we cannot substitute land resources. We need to eat. That's the problem. That's what everything makes so hard. Today, the entire economic system actually is built in a way that we use more and more biomass. We produce more, we consume more. And this is a problem. This is what chapter 8, which was analyzing the underlying mechanism, was summarizing here. We need to find another way of economic development. And we cannot come here and just say, okay, let's eat a little less food and let's use a little less forest for energy or something like that. This needs to be effective big. And in order to be big, it needs to be a fundamental change how we work in society. That's the big challenge ahead. And this is one of the conclusions of the assessment report we found here. We know that more biomass goes in conflict with carbon storage. We did not discuss so much about biodiversity, but more biomass means more areas as plantations. It means a higher biomass intensity. There comes the information of the assessment report, and it means more biomass also affecting the other planetary boundaries, and I brought you a scheme by Richardson on that. Furthermore, if we lose a lot of land for land sealing for infrastructure, what happens? And we have climate change, we will exacerbate these challenges. And therefore, and as I will skip the last slides, to enable this transformation, it's a massive one. And to get such a massive transformation workable, we need very good levels of governance, let's say it that way. We need transparent and democratic processes. We need really to look at these trade-offs and to look at the hidden interests people have, be it for whatever, be it for profit, be it for ownership, be it for power, but we need to be very transparent and open here. Otherwise, such a transition is doomed to fail. And so this is discussed in some of the chapters, chapter 6 and chapter 8. A transformation of this kind can only succeed if the land users, the stakeholders are not left behind. We cannot change the system so dramatically and just say, okay, you farmers, do other things now. Yeah, we have to be very careful here. It's a fundamental change. Climate change forces us to these things. And with that, I brought some other slides. I just want, this is actually interesting. This should be thank you very much. With this, I want to end and show the list of people writing in this chapter 2. Thank you very much. Quite over time.
Yeah, thank you very much for the presentation. And now we come to the Q&A session. So if you have any question or some points for discussion, just raise your hands and I'll come over with the microphone that also the online participants can hear you. And if the online just type in the chat, then we can ask it with the mic. Yeah, and if you want to have some of the printed ones, you can, Ingo is handing over them over there. Yeah, some questions from your side. Maybe an icebreaker question
is good.
from my side.
But there is one hand. Look.
Oh yeah.
There is one.
Hi. Thank you very much for the presentation. I'm wondering if you can tell us anything about peatlands, because I'm interested in that kind of land use. We are talking about carbon sinks, and peatlands are quite good at this. And you talked about forests and agricultural spaces, but what about peatlands? Can you tell us anything about it?
In general terms, peatlands, I skipped it a bit because that's not my field, and I heard that you covered peatlands anyway last time. Peatlands, kind of from a today's perspective, has a problem. Let's put it that way. Yeah, There is a lot of carbon to be stored in peatlands per square meter, per area. But the extent of the current peatlands is almost inexistent. It's very, very small, which does not mean that the potentials are small. There is a high potential to get much, much more area into peatland restoration. Yeah. The thing is, if we really want to go big, and we can go big, we immediately run into the problem with agriculture. Because the most fertile agricultural soils, more or less over entire Central Europe, are built on former peat or wetlands, which are drained, have been drained hundreds of years ago. So if we go big, we have these problems. If we stay small, it is one of the minor contributions in very simple terms. And there is another thing, science tells us there are some new effects that when we start re-wetting peatlands, that there might be emissions, a very strong peak of emissions of N2O and CH4 first, which then only later on will be reversed by the slow growth of peatland. And this is another thing which is important to keep in mind. The climate crisis, and I say this before, I'm not against peatland restoration. It might sound like that, but on the contrary. But we have to be also very modest in our expectations. Peat growth is very slow. It took thousands of years to build up these peat stocks. We cannot accelerate this process. To a certain degree, yes, but it will stay a small process. And the challenge here is we need somehow quick fixes. We need something which is working right now. At the moment, we have afforestation is small. Reducing harvest is quick. Dietary changes is half-half. Yeah, something like that. But in the end, and I say it again, I'm not saying we should not restore peatland. On the contrary, particularly also for the nexus climate and biodiversity. But it is not the silver bullet which will save us out of this big climate disaster we are sitting in here. Okay.
Other questions? Maybe for clarification on the wood, you suggested to decrease the harvesting and to have more old trees. So that was the message. So
kind of.
But I've also learned that younger trees have more production by producing wood in the young age. They produce more wood. So why is it not better to cut them earlier and store the wood maybe in buildings or in
Yeah, the thing is it's in the end not such a complicated thing. First of all, this is like humans. You see, when we are small, we grow quickly. When we are large or old, we don't grow anymore. Yeah. But in the end, everything is about how much carbon do we keep away from the atmosphere. If we are big, we keep a lot of carbon stored in our bodies. If somebody growing quickly is still keeping not so much carbon away from the atmosphere. So this is the first thing. When we keep forests young by shorter rotations, we reduce the carbon stock quite drastically. And these carbon stores are only about half to 1/3 what we store in a normal rotation forest. And this is only 1/3, 2/3 of what we would store in a untouched forest, let's put it that way, yeah? And the other thing is, and this is the problem, if we take wood out of the system, of the forest, usually we only take about 20%, even less, to long-lasting materials. The rest goes into very quick turnovers. We burn it, and this is carbon which we release. We put it to paper, and this is carbon which we release. There is some recycling, but most of this goes to the atmosphere. And then, and this is the mathematical backbone of everything, if you do the calculations, the emission factor of biomass. So how much CO2 emissions per unit of joule you gain, per unit of energy you gain, is about twice the emission factor of oil. It's more than twice than the emission factor of natural gas. Well, I don't like to call it natural gas, fossil fuel gas. It is in the same area than brown coal, not even stone coal, not even hard coal. Why? Well, in the end, what is brown coal? Brown coal is biomass which is not so rotten. So that this is the problem. So if we move 1 ton out of the forest and we burn it, we only replace half a ton of fossil energy. That's the big problem what we have. That biomass is such a, climate-wise, such an inefficient energy carrier.
But would there be some chance for reducing this turnover to somehow deposit the...
I think the challenge is here manifold. First of all, for the quick fixes, and it's all time is of the essence if we wish, for the quick fixes, we need to put some forests out of the use. Then we need to reduce, we could, as kind of we need, well, who is we, who is need? We could put a lot of energy now burned, wood energy now burns to material uses, to long-lasting material uses, to increase the fraction of, technically, this is a technical challenge, to get more compartments of the wood, of the tree, into the buildings in long-lasting things. And in this moment, we have one. And we have the options. We can reduce particular room heating, which is the 90% of the application of wood fuel or even more. We can get rid of that. So we have the thermal pumps. We have many systems where we can get much more efficient as room heat. So it's not that it is an essential resource. It's a little bit different. Depends, of course, what you deem essential. But with liquid fuels, if we phase out fossils, and we still want to travel with planes, we will need liquid fuels, and they will have to come from the land if we don't use fossils. Yeah, but then we kind of, as society, we decide this is essential because we don't have another option. There are no planes which can fly with batteries at the moment, at least. Yeah, but in general terms, that's where the intricacy lays. Yeah. If you wish. It all has to do how long is carbon staying away from the atmosphere. And we are sometimes, how to say, I can tell you a little anecdote as there are not so many hands popping up at the moment. This is what we call in this type of science a stock flow system. So there is a flow coming in, a flow flowing out, and the difference of these flows is a stock buildup or a stock loss. And there have been and forests operate like that. I just want before I wanted to explain this. We have the increment, we have the mortality, and we have this balance. And there has been psychological research, which is also going on, which has a finding, a syndrome of how human brains work, and this is called the stock flow failure. We humans do not easily understand changes of stocks. And intuitively, we will always look at the fluxes. But when it comes to climate change, when it comes to climate mitigation, it's all about the stock. It's about the stock in the atmosphere and the stock outside of the atmosphere. That's how to say the key to everything. But we humans are not able to nicely understand, even trained people. They have these stock flow failure tests. They were with medicine students because they kind of made tests about letting people guess what the concentration of certain substances of blood are by taking the metabolic rates and by the influxes, and 90% are wrong. Because we think if we have the bathtub, this is the typical example for these type of things. If we have a bathtub and we increase the inflow of water, the stock will flow up, will go up. So the bathtub will go full. In principle, this happens, but this happens only if we keep the outflux stable. If we increase the inflow and the outflow, it can even happen the exact opposite. The stock will go down. But our brain is not made to understand this intuitively. And this is the same with the forests. And this is the same with the keeping forests young so that they sequester a lot and grow, or keeping them old so that they store. And in the end, climate-wise, it's quite clear, but in the end, nobody will say, and I'm the least one, saying we should not build stuff out of wood. Wood is a perfect, nice resource, everything. but we have to understand it's a scarce resource. It's something where we should make the best uses out of it and not just burn it. And there are many applications today, and it is particularly in the building industry, it's a very big challenge to increase these 15 to 20% up to something like 25 to 35%, because that is something when we see then climate change benefits.
And there's some difference in eco-service of young woods and older ones.
Of course. And there are many differences, but just to say also with biodiversity. But we know with biodiversity forestry, the forest management has a big problem because biodiversity in a forest is usually very high in the very early stages and in the very late stages. And in the middle, biodiversity is relatively intermediate to low. Yeah, and therefore we have practices in forestries like, I don't know all the English terms, like deadwood islands, Totholzinseln it's called, deadwood islands, that we have mosaic stones that species can jump, and most of the biodiversity stuff is related to the deadwood. And now we have a silvicultural practice developed where there is almost no deadwood in the forests. We get rid of everything because we learned about the bark beetle and we learned many things. But there are also other ways to fight the bark beetle than just to get the wood out. But the moment you pay a lot for biomass energy, we will take the dead wood out because people own it and people will earn money. So this is also, how to say, this is a societal challenge to compensate for these benefits or kind of to pay for these ecosystem services, if you wish. Okay?
So questions? If you look on the online. No questions at all.
Okay.
So, well then.
If not, otherwise drop me an email. There is no email here, but I'm sure you will.
Yes, I can provide. And yeah, you'll find the slides on OLAT. Thank you for
my pleasure.
Your presentation. Thank you for coming. And the discussion, and be aware of the change in our program next time. And yeah, see you next time in the lecture series. Thank you very much and goodbye.